Okay, we're recording. So hello everyone, welcome to our snack seminar for this week. It's a pleasure to introduce Galen Wilkinson, who's a PhD student jointly actually, or maybe not officially jointly, but in any case, for all practical purposes, jointly between University of Surrey and Imperial College London. I think you're at the latter today, correct?
I'm at Imperial, that's right, yep.
Yep. And so Galen's got a really interesting background. He's worked in a lot of places. I remember we talked about this a couple of weeks ago, but I didn't realize just how many until I looked at the profile you sent through. You've worked in the US a little bit at Maryland, NASA, NIST, Uni of Washington, Johns Hopkins, Northeastern, and so on, as well as a little bit at TU Berlin and the private sector in Germany, private sector in Italy, and so on. So you've got a really interesting background. Your areas of work and research have included parallel and high-performance computing, complex systems in general, data science, robotics, and so on. Today, specifically, we're going to be looking at cascades, or which you could also call bursts, but in artificial neural networks, and looking at how we can characterize computation in terms of Boolean functions from them. So this should be quite interesting. It's a nice talk at the intersection between neuroscience and complex systems. So over to you, Galen.
Yeah, great. It's really wonderful to be here. And yeah, today I'll be talking about spontaneous emergence of computation in network cascades. Don't bother reading the abstract. I'll tell you about that. Let me see if I can advance. Here we go. Okay, so this is together with Henrik Jensen at Imperial College London. He's head of the Center for Complexity Science, which is where I am right now, and with Sotiris Motianis at University of Surrey and Department of Computer Science. Okay, so I'll give you an overview of where we're going. So basically, first we'll talk about cascades and computation, and we'll talk about how universal cascades are. They're really everywhere. It feels like a very fundamental process kind of in the universe, really. We'll talk about the linear threshold model, and the linear threshold model is a very simple model, network model of that has this cascade, this critical cascade behavior. Then we'll talk about how the LTM computes logic via what I'm calling logic motifs. I'll explain all of this, and then we'll show how you can get actually cascades of antagonistic nodes. I'll explain that. That compute a universal basis, which means it gets you any Boolean function that you want. Then we'll look at the statistics of the attractors in the Boolean space, kind of in the phase space of the networks. We'll talk about how we get a rank ordering of the function frequency according to the complexity of the functions. And then finally, we'll look at these relationships between the symmetries of the functions themselves and their complexity, and how that relates to their frequency, their observed frequency. Okay, the writing here is a little bit small, but hopefully we can read it. So first of all, cascades are seen in many domains, to the point where for me, I would be very surprised if you showed me a naturally occurring network and you said it did not have cascades. I might not believe you. So of course, in the brain, we have neuronal avalanches. But also in social networks, we have epidemics, which we're very familiar with by now, where one person gets sick and you get this sort of wave traveling across the network, the spreading process of infection. But then you also have information diffusion, sort of rumor spreading, transmission of ideas across networks. Things like viral marketing take these cascades into account now. To the point where in computer science, this has become a formal problem called influence maximization, which is basically like, who should I influence in order to spread an idea, a desire for a new product or something like that. But then also they happen in physical and chemical systems like sand piles, as we see here on the right. You can, chemical cascades. I mean, you can just keep finding new examples of them all over the place. So you really see this Venn diagram that you're really at the intersection of many domains when we talk about basic cascades, information cascades in particular. So again, yeah, you might call it a branching process. It's related to percolation, and I'll show why, which is again one of these very fundamental processes. Also, it's nice to think about it in this way, that, if you think about a system made of elements and you can perturb or not perturb each element, and that's kind of what I've started thinking of as a point bit. You have this point and you can either perturb it or not. And then you have these interactions between the elements, which you think of as edges or connections in a network. But I have started to think about it almost like an interaction bit. This is just a side, mentioning these on the side, but you might have, so again, when you have any system made up of some elements or agents or units, and they interact, you can then build a network out of them as a model of that system. And you can then get these patterns of perturbation going on, and these interactions of perturbation patterns, which conveniently are what we call Boolean functions. And luckily, there's this large literature about Boolean functions and Boolean logic. So you really start to feel like you're doing this basic research into the physics of kind of how systems process or even maybe create information. So that hopefully gives you a background and a really compelling motivation for me that always keeps me excited. Okay, so let's start out. We'll talk about percolation. This is not something we came up with. This is a long-standing idea, especially used in things like statistical physics and theoretical computer science. And the idea is that you build a random network, what's called an Erdős-Renyi or Erdős-Renyi-Gilbert random network, which has n nodes and has a connection probability p between any two nodes. Okay. And over many trials, you gradually increase the connectivity. Connectivity can also be considered as the mean degree, which means the average number of network connections that each node in the network has. So does it have 3? Does it have 0? And you can gradually turn up the connectivity. Just think of the x-axis as how connected the network is. And then you can look at the size of the largest connected component in the network. So that might look like something on the left here, where you have this big blob of nodes that's connected, and then you have all these smaller components that are disconnected. So that would be the largest connected component. So you can, over many trials, gradually turn up the connectivity, and at mean degree 1, so when on average each node has one neighbor, you get this phase transition. So the size of the giant connected component, the largest connected component, suddenly explodes around mean degree 1. And this is a very typical behavior here. I think I did it over 10,000 trials for each connection value on a large network, 10,000 nodes. So that's percolation when you have this phase transition. And also recall that you get a scale invariance of the component size. So you get this power law distribution of the component size. So you have one large component and then kind of several slightly smaller components and so on. So you get this huge cloud of disconnected of singleton component. That'll come up later. So now let's get to the linear threshold model. So again, this is a very simple, probably one of the simplest models that has this cascade behavior. So again, so this is a different model. So here, again, we create a random network. So an Erdős-Renyi network, like we have on the left. I don't know if you can see, this is actually time progressing to the right. Yeah, the little window of people might be in the way here, but so you build your random network. Each node also has a threshold value between 0 and 1. It's uniformly distributed. And then nodes can be labeled or unlabeled. So we start out unlabeled here would be the white color, and labeled would be black. So you start out with everybody unlabeled, and then you pick one node to label or activate or perturb. And now we go around to each unlabeled node and we ask the question, what fraction of your neighbors are labeled? And if that fraction reaches our threshold, then we become labeled. So if let's start out here, we label this node that has threshold 0.97, and now we go to the next time step, and we happen to choose this node that has 0.45 as the threshold. We say, okay, well, 1/2, so 1/2 of its neighbors are labeled. That's greater than, is that greater than or equal to my threshold? Yes, it is. So I become labeled. Okay, and now we, just to go a little bit further, we look at this node that has 0.37 as a threshold. You can see my mouse, by the way, right? Yeah.
Yes.
Okay, so you go to the node that has 0.37. You see that 2 out of 4 of its neighbors are labeled. So of course that's 1/2, that's 0.5. That is again greater than or equal to my threshold. So I become labeled. Okay, so we just proceed in this fashion, say, you know, what fraction of my neighbors are labeled. In this case, the cascade happened to cover the entire network. So you would say the cascade size is 1, which means 100% of the network is covered. And of course, that doesn't have to happen. Sometimes very small chunk of the network can be covered. Notice that if we look down here at the bottom, we can write this in a vector form, which can be very convenient. You know, it's convenient for programming, for running these networks, but it might also be convenient for putting them in a framework of machine learning, because typically that's how you write a lot of machine learning or like deep learning kind of operations or processes. Okay, so notice that if we have a node that has threshold 0.45, and if it has 2 neighbors, it's sufficient if one of its neighbors becomes labeled, that will be 0.5. So 1/2 of its neighbors will be labeled. So that's sufficient for this thing to become labeled. So you can imagine a situation where you have many nodes that have a threshold that's low enough that all it needs is one neighbor to become labeled for it to become labeled. And so Duncan Watts called these vulnerable nodes. So you have these nodes that are very easily influenced. And he said, well, look, when we connect nodes, just like with percolation, you know, if you keep connecting nodes, you can get this emergence of a giant component of vulnerable nodes. So these nodes are, you know, if you light one on fire, the whole thing will burn because they're touching the giant connected component. So that's how you can think of this as percolation, that, you know, if you get a large enough connected component of these vulnerable nodes, then you'll get a large cascade. And so that's the connection between percolation and the linear threshold model. Hopefully that's clear. Okay, so now we've seen the LTM and how it's related to percolation. So let's look at a very small linear threshold model. So we'll look at this top little network of A, B, and C. And we're really only looking at C. So we think of A and B as input perturbations, okay? And we can perturb them according to the left-hand 2 columns of this truth table. So, you know, 0 means not perturbed and 1 means perturbed or activated or labeled. So 0, 0, nothing, you know, nothing's labeled. 0, 1, only B is labeled. 1, 0, only A is labeled, and 1, 1, both are labeled. Okay, and then we can, each time we can run a cascade and look at this tiny mini cascade and see what happens to C. Well, when the threshold is less than or equal to 1/2, then C will be, in this case, vulnerable, very easily labeled, easily, you know, activated. And it turns out that the pattern of its activation exactly corresponds to OR. Well, the moment you see that, that should open a whole can of worms in your mind, right? Because obviously, then if we look at the next figure below, if the threshold is greater than 1/2, then we get this activation pattern, which is exactly equal to AND. Okay, so that's very compelling, right? Suddenly we're computing logic. And again, these, you can think of these as little logic motifs. These are little subnetworks that will perform a function. And so we get OR and AND, logical OR and AND, okay? And also notice that this is quite similar, if you know about like McCullough-Pitts neurons, it's quite similar to those actually. You know, we have this very simple threshold and we're activating based on our inputs. So it's very similar to early neural networks or deep, what you might call deep learning now. Well, we have OR and AND. So if you're maybe a computer scientist or someone like that, you might say, oh gosh, we have OR and AND, wouldn't it be nice to have not? Well, I was sitting there in a library in Italy, and I was thinking about this, and I was like, oh yeah, we can get nod. We just create a new kind of node. So we just take the logical complement of our original labeling rule. Remember, our original labeling rule was this sort of excitatory rule. We said if our fraction of neighbors labeled is greater than something, my threshold, then I become labeled. Now we'll just cross that out and take the exact logical complement. If the fraction of neighbors labeled is less than our threshold, we'll label you. So we created a new kind of node. We'll call this node an antagonistic node. So it's sort of takes the complement of the original node. And now if we make C instead one of these antagonistic nodes, and we keep everything else the same. So all I did was swap out that rule. Then our OR becomes NOR and our AND becomes NAND. Okay. Now, again, if you're a computer science person or something like that, you'll immediately say, oh, that's amazing. Now, when I compose functions, I can get any logical function. So that's a well-known fact in computer science. You know, if you compose NORs or if you compose NANDs, you can build up to any Boolean function you want. So you have a bunch of other Boolean functions besides AND or you have XOR, you have, you know, NAND and all these, or yeah, many other Boolean functions. By the way, you still do get cascades. So you're computing these now with cascades. So that's very interesting because you're doing Boolean logic, but you're doing it in this, again, in this sort of percolation, this information diffusion kind of way. And this is an example of one of the Boolean functions you can get. You can actually get a half adder using these NAND, these are all NAND gates. And so you can actually get a half adder. Half adder is doing bit summation where you carry the one. It's kind of like in base 10 when we carry the one, you have to do the same thing with bits. And so I guarantee your computer or your smartphone is doing a lot of these operations all the time. So it's one of these fundamental things. But anyway, this is just a slightly more complicated Boolean function that you can do. So it gives you an example of that. Okay, so let's zoom out a little bit and think about this. So imagine this is a schematic, but imagine you build a network and you say, okay, I'm only ever going to perturb these two nodes A and B. I'm not going to perturb anything else. Those will be just the result of the cascade. So if I iterate through A and B, just like we did in this truth table, like here, for example, 0, 0, 0, 1, 1, 0, 1, 1. And each time I clear the network and then I clear the states of the network and I run a cascade, I'm going to get some activation at each node. I'm going to get, the columns like this sum column, for example, I'll get some pattern. And that pattern must map to one of the Boolean functions. Okay, call it F1, call it F2, call it F3. So I'll get some Boolean function. So I'll get this cloud or this sort of distribution of all these Boolean functions being calculated in the network as I run through my input perturbation possibilities. Okay, so yeah, I create the network, I freeze the edges, and I freeze all the thresholds, and then I just clear each time I clear the state of all the nodes. I run a cascade on those inputs. So I'll get these cascades, which are computing Boolean functions in the network. That allows us to change the way we think about networks. Okay. So now when we see this picture here, what you should think of is this is a little function. Each of this is sort of a cloud of functions, like a bunch of little automata. And of course, Joe, it makes me think of you with the cellular automata. These are almost like little, they look even a little like the gliders and things like that you see in cellular automata. And really, I think it's reasonable to put them on a similar framework and say, okay, wow, now my network is just like in a cellular automaton, my network now has all these little logic automata, and it's very similar to importing or calling a function in Python or something like that. These are functions ready to be imported, and the way you import them is you connect to them, and then your cascade will include those, and that's a very coherent, it's a very sort of concrete way. You can think of, oh, I need this function over here. Okay, it has a certain bunch of thresholds and connectivity, which computes a certain set of functions. Okay, so that's really a nice way to think about it. And I was reading this lecture by von Neumann it's actually from 1952, published in 56. And I read this, don't read this paragraph, but what he says was like, wow, this applies exactly to what's happening in these networks. So we're going back like however many years, 60, 70 years or whatever that is, back directly to von Neumann and Turing and things like that. And again, these are these logical automata being calculated by these sort of logic motifs. So I think that's a very nice intuition. Okay, so let's look at the Boolean functions themselves for a minute. All right, so if we have two inputs, here are all the possible, each column here is a Boolean function. I can compute the 0 function, I can compute which is always false, I can get the one that's always true. Function number 1 is and, function 7 is or. You can take my word for it, but so it turns out that the LTM, since it has that excitatory kind of rule, the original LTM, not the antagonistic one, you can only get the green functions 0, 1, 3, 5, and 7, which are, by the way, these are what are called monotone Boolean functions. So as I increase the number of true inputs, the number of true outputs cannot decrease. So for example, and if we look at this green plot on the right, I increase the true inputs and I need both of my inputs to be on in order for my function to be on, and or is sort of similar. Now function 15 is actually technically monotone, but notice that with the original LTM, the 2 seeds are off. The 2 seeds are not activated, so I can't get a 1 here. Okay, that's why I can't get function 15. So anyway, I can get these other monotone functions. Okay, I can't get anything else. Okay, and another very interesting fact, or sort of a brain teaser, is that let's look, this truth table, we have only 2 inputs, so k equals 2. The number of columns, the number of functions that what I get on 2 inputs is 2 to the 2 to the k, which is 2 to the 2 to the 2, which is 16. Okay, 2 to the 2 to the k is called a double exponential function, and it grows ridiculously fast. So this is a log plot, and for those of you who are familiar with this way of looking at things, as I increase k, this is either k or n, so the blue curve here is going up like this on a log plot. That means the order of magnitude is increasing like crazy. That is so fast that it compels you to really sit back and think about things in a deep way. Just to compare, so remember, well, okay, I'll talk about it in a second. So also, meanwhile, the number of networks on n, so if I have n nodes, so 100 nodes or something like that, the number of possible networks is 2 to the n times n minus 1 over 2. So that grows like this orange curve, which is still actually pretty fast, but it's still very slow compared to the number of functions. So you can kind of begin to think about this in this sort of war between these 2 combinatorial spaces, like the interaction of these 2 combinatorial spaces. Like how does the network possibly compute a particular function? So if you're a machine learning engineer, you might typically want your network to realize a particular, I want function number 13 to appear in my network at least once, or maybe 100 times. I'd like that function. Well, remember, here we only have 2 inputs. So if k is 5, then the number of functions goes up into the billions already. Okay, so so good luck getting your network to compute a particular function because the space is massive, right? So it starts to become pretty interesting. Like, how do I get my network to navigate toward a particular function, or how does a naturally occurring network do that? That's kind of the area where we're operating here. Okay. I think I'll skip this slide. It's not that important. Okay. All right. So then we can, of course, build an LTM network, and we can look at the number of unique functions that it computes. So I build I build a network with 1,000 nodes, and I can then look at each node and say, oh, this computed function number 3, this computed function number 1 is, and I can tally the number of unique functions that I see in the network. Now, this is a bit of a toy model, and this plot is grossly unhelpful. Because we see this sudden explosion at a very low connectivity. Remember, Z is mean degree. So I connect the network a little bit, and suddenly I get all 5. Remember, I only had 5 possible, those green functions in the truth table. I had 5 possible functions when k equals 2, when I have 2 inputs. But that's okay. We're in this toy example. So we can ask, like, what happens just, maybe slightly after that percolation, that number of functions explodes. And we can look at a network or an ensemble of networks actually, and see what is the distribution of the function. So I get function 3, 5, 7, and 1. Remember, 7 is or, 1 is and, 3 and 5 are two other functions. And I get this very skewed distribution. This is on a log scale on the y-axis and a linear, you could say a linear scale on the x-axis. So when you have this shape, if you had a line here, an exact line, you would say that's a decreasing exponential, okay? So it sort of looks like a decreasing exponential, like it's a very skewed, very compelling distribution. And so let's try a larger value of k. Okay, so when I increase k to 4, so when you have k equals 4, in theory, your truth table has 65536, so 65,000 possible functions. Now, only some of those are monotone, less than half are monotone, but still, it's a lot of functions, okay? So when I ensemble over I create many networks and I look at the distribution in that ensemble of my functions, I see this very compelling, what looks like a decreasing exponential distribution, okay? So this looks quite linear on a log linear plot. Okay, so then of course you ask why, how am I getting this? Why am I getting this, what looks like exponential distribution? Okay, so let's go back to the truth table. Let's look at the simplest possible function, the 0 function, which gives you, basically it always gives you false. It's really the most boring function in the universe. So no matter what you give it, it always gives you false. Well, the easiest way to get that in the network, if node U here is the node computing the function, and A and B are again your inputs, okay? The easiest way to get it is just to have no path from U to A or B, and U will just sit there in the LTM, U will just sit there and give you a false every time, okay? My fraction of neighbors labeled is 0, so that's it. 1, the AND function, well, I need to know the information about A and I need the information about B. So the only way to get that is if I have a path from A to U and from B to U, okay? I also have that threshold requirement, but I would say that this path, okay, near criticality. So when you just barely have your connected component, your giant component, the network is very sparsely connected. So everything is very tenuous. So having a path is actually a significant event. And I would say it's much more significant than this threshold in terms of the probabilities of this function occurring. These other functions are, okay, so this is f of a comma b equals a. So if we look at this function here, notice that this column is identical to a, meaning all I have to do is get the information of a to compute this function. So that's all I need. I need just that path from a to u. I don't need b at all. So I need one path. Here I need similarly a path from b. And here I need a and b again, because this is or, okay? I just have a different threshold value. So these are arguably the simplest little motifs or logical automata that'll get you these functions. Okay, so that's good because that helps us build a probability. And here we're talking about proportionality. So there are other factors in the probability, but we'll be happy if we can get this one. Okay. So for F0, it's going to be proportional, just the probability of not having both paths. So 1 minus the probability of a path, whatever that is, squared. For F1, I need both paths. So that's P of path squared. And similarly, again, this one, each of these, we said we need one path. Here we need, this was or again, I need both paths. Okay, so it's probably something like this. Seems reasonable. So of course, then we ask, well, what's the probability of a path? Gosh, I don't know. I have no idea. And I was really stumped by this at one point. But then remember, we're in this percolation context. Okay, so it turns out that especially in what's called the thermodynamic limit. So as the number of nodes goes to infinity, this becomes exact, but let's forget about that. So just in a large network, like 10,000 nodes or even less than that, basically you only have a path if you're both in the GCC. So you're either both if you want to connect between some node U and some node V, the only way to do it is if you're both in the giant connected component. Otherwise, the probability of connecting is incredibly low. Okay, so you can kind of treat this as absolute as soon as the network is larger than a couple thousand. And so that's very helpful because we have a closed form function due to Mark Newman, I believe, it's in his book anyway, where we have this closed form which we can solve numerically, which gives you the probability of a random node belonging to the GCC. Okay. So I won't go into that now, but that's very useful. Okay, because now I can think of my probabilities all in terms of this. Okay, so just going back to the motifs, if we compare, so we can look at the relative probability. Remember, I had those terms like those expressions p path squared or p path. So I can, if I can rescale those and just look at the relative probability, and I see that there is this relatively high correlation between the observed frequency, so the distribution of the frequencies of these functions in the network, and the probability of the paths from those motifs. If you remember when I drew the little networks and I derived my probability. So this looks very promising. This is when, let's see, here I believe k equals 4. So this is a confusing plot, but the black line is the observed frequency. And the p path, so this is from those motifs, and this is rescaled, but anyway, it looks like there's still a pretty good correlation between the predicted probability and the observed frequency, and that has a Pearson correlation of 0.74, and it fits an exponential with this r squared of the frequency fits an exponential with r squared 0.88. So it seems a reasonable starting point anyway. Okay, so now things get really interesting for me. Okay, so there's something called, I didn't go into it actually because I skipped that slide, but I'll talk about it now. So there's something called decision tree complexity of a Boolean function. Okay, so let's start with the zero function here, this left-hand column. So notice that, again, as I said, this network will compute that function, and notice that the number of required paths here is 0. Also, if we just look at this function itself, how many decisions do I need to make to evaluate this function? Well, 0. The depth of the decision tree is 0. I don't have to know anything. I just say 0, false. For the function and, I required 2 paths, if you remember that. And if I look at the decision tree, and here I've only drawn the true branch, I need to ask, is A true, or is A greater than 0? And is B greater than 0? And if those are both true, then the function is true. And so the depth of that decision tree is 2. Okay, and you can compute the depths of these other decision trees as well for these other functions. So that's nice. That's very interesting. And the number of paths is equal to the decision tree, seems to be equal to the decision tree complexity. Now here's where, to me, it gets really interesting. Let's look at the Hamming cube representation of these functions. So what we do is we take the input values, so A and B. So here is 0, 0, and we map 0, 0 to this corner, 0, 1 to this corner, and so on. We can make the corners of this cube, okay? And now we put the matching, the corresponding function value on the corners of the cube, okay? And so I get this cube here. Notice that if I flip this cube vertically, so I just flip it, so that these end up at the top and these at the bottom, I get the same function on the inside, okay? Same, if I flip it horizontally, I get the same function. So I can flip this, it has two, you might call it 2 axial reflection symmetries. But anyway, I can flip, what it means, I can flip it both ways, horizontally and vertically, and I still get the same function. This one, this is and, if I flip it vertically, I get a different function. If I flip it horizontally, I get a different function. If I just, vertically, I'll get 0, 1, 1, so 0, 1, 0, 0. And if I flip it horizontally, I'll get, again, 0, 1, 0, 0. So I get a different function. So it has 0 axial reflection symmetries. So that's a really nice way turns out to get the decision tree complexity, because it turns out that the decision tree complexity is the complement of the Hamming cube symmetry, which lets me come up with an algorithm for computing the decision tree complexity of a function. And that's useful because if I have 10 inputs, if I have k, so instead of just a, or if I have 5 inputs, instead of just a and b, I have a, b, c, d, e, I'm going to have these really messy functions. You know, those columns are going to be long, they're going to have a lot of zeros and ones, and I'm going to have to figure out a way to know the decision tree complexity. Turns out I can just flip the Hamming cube along the axes, and that allows me to get the depth of the decision tree for that. So that's a complexity measure on the function. Now that's really nice because the relationship between, once I have the complexity, I can say how many nodes need to be in the GCC. Okay, so for example, just ignore the writing, look at this picture. Imagine I need 2 paths, and like the function and, for example, I needed 2 paths. I need a path from A to U and from B to U. Well, notice, like I said, in that case, all 3 nodes need to be in the GCC. And notice the number of nodes is 1 more than the number of edges. So I have 2 paths, so that means I have 3 nodes. So basically I can get the decision tree complexity of the function, and I can add 1 to it, and that's the number of nodes that need to be in the GCC. So then I can write my probability proportional to that probability, the probability of that number of nodes, in this case 3 nodes being in the GCC. Okay, notice that is a decreasing exponential because p is almost always going to be less than 1. Okay, so the probability of being in the GCC is some small number less than 1. I'm raising it to some power. Okay, that's called an exponential. Just our base is not e or 2. It's this whatever the probability is. Okay, but it's an exponential. So that's interesting. So that explains why we see that. That may explain why we see that distribution. Okay. So just to give an overview, again, we can compute the complexity using those Hamming cube symmetries. Then I can say, oh, the number of nodes that need to be in the GCC is just 1 plus that complexity. And then I just say that, again, the probability of the function is proportional to the probability of being in the GCC raised to that power. Sorry, I'm giving a talk. Okay, sorry, the janitor was here. Okay, so, all right, so I hope that's clear-ish. Anyway, the point is, from the function itself, we now have, just looking at a Boolean function, we're able to kind of estimate the probability of getting it in these random LTM linear threshold model cascade. That's a takeaway. Okay, and sure enough, if I plot, okay, so here the blue is again the frequency, and the green is the complexity. And so there's this direct, complementary or sort of inverse relationship between the complexity of a function and its observed frequency. And notice that's the spontaneous emergence of complex functions right there. We got them, all we did was wire this thing. We made random thresholds, we randomly wired the thing together, and we still got complex functions. So Henrik Jensen, when he saw this, he was like, oh, that's really interesting. Like, we get complexity without doing anything really, just randomly wiring things together. And again, that was the toy model, but we see it also, when k equals 4. So that, again, number of inputs is 4. So we have a lot more functions. And this is not exact, but we definitely see this upward trend in the complexity. So these complex functions are rare, and they're logarithmically rare. They're not just linearly rare. They really are quite, it's a very skewed distribution. Yeah, so what I skipped earlier was just that if you take the truth table of all of the available functions, so let's suppose I make remember you have that table with all the columns. So if you take, k equals 4, for example, so you have 4 inputs and you have this long, you have 65,000 columns in your truth table. In that case, you can go through and say, okay, what's the decision tree complexity of each function? And then you can plot the distribution. And that's what I did. And that's how I got this plot. And notice this is curving upward. Okay, so in other words, most functions are really a lot of the functions are going to be complex. So if I look at some large truth table, k equals something, even not that big, I will see most of my functions are complex. Okay, so so this decreasing exponential is even more surprising when you consider that most functions are most of your available functions are complex. That was the point. If you don't get that, it's not that important. But okay. So another way we might look at this, if we remember, this is our network near, when we have the formation of the giant component. So we might say, look, maybe there's some Pareto optimality going on near criticality, because I can have complex functions, which would be going on inside of this GCC, right? Inside of these larger networks. That's where I can get these complex functions. But I can also have diversity. And remember, each node here this is a cloud where each node has a different threshold, okay? So I get a bit of both near criticality, because I get some complex functions, but I also get a lot of diversity, okay? So I almost wonder if that's what's going on, near criticality. There's this thing called the criticality hypothesis in neuroscience, that, networks seem to operate best. There's lots of optimality going on near criticality, and you might say, okay, well, at criticality we're poised where we can go in a lot of different directions because we have diversity, but we also have some complexity as well, right? We're not starting from nothing, so we're poised at this tension between these two things. So that's a really nice intuition that sort of came out of this. Yeah, so I could easily, near criticality, it's easier for me to rewire and get different functions, and some of them will be complex. Whereas if I weren't, imagine this thing were really disconnected, well, then I wouldn't have anything. I would have diversity, but I wouldn't have any complexity. And also, if it was really densely connected, I would have complexity, but I would lose some diversity because my network's already committed toward a certain direction of certain. Remember, this Boolean function space is huge, so I've already committed toward a certain direction when I've already wired the thing together, right? So I hope that makes some sense, but that was a really nice result. Okay, so we looked at the green functions, the monotone increasing. Similarly, you can look at the monotone decreasing functions. Okay, so those are the ones that are increasing as the number of inputs, true inputs increases. Anyway, basically they're tending to go down. They're tending to have more false values as you increase the true inputs. So NAND and NOR are two good examples, and they're not that exciting. You get very similar motifs. You're really just reflecting across this truth table. It's kind of cool, but it's, you can derive similar expressions for the probabilities, and you go through the same kind of thing that we've done. So I won't go through that now. But what is more interesting is XOR. If you're a machine learning person, you know that there was this dark ages of, Minsky and others put the kibosh on XOR. They said, oh, deep learning can't work on XOR, and so XOR's got this history as one example. But XOR is a more complex. You could think of it as a bit more complex because it's non-monotone. As you increase the number of true inputs, it goes up and then it goes back down. If you look at, let's see, I always forget. XOR is 6. Okay, so I have 0 input, 0 true inputs, things false. I have 1 true input. I get a 1 here, it's true. And then if both are activated, I get a false again. So XOR is a bit weird. It looks a little bit like an oscillation. Anyway, notice this is arguably the simplest network that will get you XOR. Notice it's got all kinds of things. It's got 2 LTM nodes. It's got 1 ALTM node, 1 antagonistic node. Oh, what I didn't say here in the monotone decreasing is that these I've just replaced the original nodes with antagonistic nodes. That's the only change I made. Sorry if I'm confusing you by jumping around, but okay. So in XOR, you get a little network like this. This thing's pretty highly connected inside. It looks like a little monster. You know, it's not just one node anymore. It's three nodes in the inside of the, you know, W is computing XOR, but you have these other two going on. So it's quite complex. You know, you can try to write probabilities, and you notice I need 1, 2, 3, 4, 5, 6 paths. I need 5 nodes to be in the GCC, so P GCC to the 5th. However, the decision tree complexity of XOR, remember we had that method, we find the decision tree complexity, so it's 2. And then we raise PGCC to the complexity +1. So that should give me PGCC to the 3. Okay. That does not equal what we see from our picture of the number of nodes that need to be in the GCC. So the point is that method of using the decision tree complexity doesn't seem to work with non-monotone functions because they have this internal wiring, basically. Probably we need a better method for estimating the complexity of non-monotone functions. Yeah. However, even though that seems to be the case, we still get this, looks like, except for these two nodes, these two functions here, it's sort of got a similar shape. I mean, it's linear-ish, decreasing exponential, and it is it's in the inverse to the complexity. So those still seem to be true, roughly. Okay, so quickly, I'll just mention a side result, which was kind of nice. I don't, maybe Joe's aware of this research, but okay, so switching channels a little bit here. Notice that I can build an LTM. And I can say I want a certain fraction of my nodes to be antagonistic and a certain fraction to be excitatory. So I want maybe, you know, 1/3 of them to be antagonistic. So the fraction of antagonism here is we're calling theta. Okay, so again, so the blue, this line here would be the original LTM. None of the nodes are antagonistic. The pink or whatever color this is would be entirely antagonistic. Okay, and then the green would be 1/3. So 1/3 of the nodes are antagonistic. Okay, excuse me. Notice that if we're looking at the number of unique functions computed by the network, so how many unique functions did we see? And Z is the connectivity. Here it was done on a log scale, but it's plotted on a linear scale, actually. Anyway, the point is that for a wide range of connectivity just above criticality, 1/3 antagonism seems to give us the most, the highest number of unique functions, okay? Which is kind of interesting. So again, if you're someone who knows about the criticality hypothesis, that's kind of interesting. So I want to maximize my number of functions realized by the network. So that's from 2 to the 3 up to about 2 to the 10. You can see it better on a log plot. This is the same plot now plotted on this log scale. So the green, the 1/3 antagonism, is giving me the most, the highest number of unique functions. Now that also goes along with research by like the D'Archangelis group in Naples and probably others, which says 1/3 inhibition. So in the brain, typically, I guess you see inhibition and the fraction varies, but sometimes it's around 30%. There's been some work by D'Archangelis and I think others saying that that 30% antagonism or inhibition rather seems to somehow optimize information processing. Well, we can go through a little, I'm not going to go through it now, but you can show that you can make antagonism from inhibition, and you can also make inhibition from antagonism. Michael Herman at University of Edinburgh told me this, and I said, oh, that's really interesting, because then basically what it means is our results for antagonism somehow can be mapped onto inhibition, and it seems like it might be even a 1-to-1 mapping. So in other words, these results of maximizing the number of functions at 1/3 antagonism may also imply that 1/3 inhibition somehow optimizes the number of functions. And so that's kind of a nice side effect of our research. Anyway, I've talked about a lot of things, so let me take you through so you remember a little bit. So remember we said network cascades are ubiquitous, are naturally occurring, and you can think of them as percolation. You get this giant component across the network, which enables the cascade to proceed. Cascades compute logic. Okay, so we showed that. We showed that you can think of these little subnetworks computing logic as these logic motifs or automata, right? So hopefully Joe's getting excited by that. You can then also make up these antagonistic nodes, which seem to be equivalent to inhibition, which yield universal computation. So you can get any function that you like as long as your network is large enough. Okay. Also, we showed how the Boolean function space is huge. Remember, as k, so for even k equals 5, the number of unique functions is in the billions already. So, how do these networks begin to navigate this huge Boolean function space? Yeah, and then we showed that we have this random network of threshold units, and we get this naturally emerging rank ordering of complexity. So remember that we had that decreasing exponential, and it was inversely related to the complexity, and that was the spontaneous emergence of these complex functions. We also showed that percolation, remember that PGCC lets us predict the proportionality of these function probabilities. And then we also showed that, yeah, there was this relationship between the function frequency, so the observed frequency, the decision tree complexity of the function, which is the depth of their tree, decision tree, and the reflection symmetries of that Hamming cube, if you remember that. So there's this really nice relationship seems to be there. And then finally was this last result, was this result for 1/3 antagonism seems to coincide with finding elsewhere and observe things in biology. Really nice sort of deeper takeaway message, which I think is fascinating, is that the formation of the giant component, you could call that a symmetry breaking, I believe you can call that a symmetry breaking event, a la Landau theory, okay? So you get this formation of the GCC. So basically you've committed the network in this certain direction. There's a lot of theory behind the symmetry breaking, but anyway, so that's happening in the network. But notice that we said it's also related to symmetry of the functions. Okay, so that's a form and function relationship. So the form of the network, the formation of the GCC somehow is related to the complexity of these functions. You get these two symmetries that are somehow related to each other. Okay, so for me, that's really interesting. I won't go into, well, I don't know, we have 51 minutes now. Do I have a little time to go into future work, or should we do some questions?
We should probably do some questions since we're hitting 5. How long were you planning to go into future work for?
It'll take probably 5 minutes. I can skip a couple of them. Okay. I think some are more interesting than others, so I'll try to talk about the interesting ones.
Yeah, if it's 5 minutes, I think we can jump into that.
Okay, I'll skip that one. Yeah. Okay, let's go to modularity. Okay, so, well, okay, I'll say this really quickly. So remember, we have this number of Boolean functions growing crazy fast, okay? Things get big. So in the future, we would like to work on, we'd like to run simulations of larger networks. You know, the brain has on the order of 10 to the 9, 10 to the 10 neurons. So it'd be nice to be able to scale things up. You know, Henrik said, look, weird things can happen when things get large, so it's useful to actually simulate them. Also, the number of functions grows ridiculously fast. So it'd be nice to scale things up, but you run into problems if you do straight up simulations. So maybe you need to start thinking in a more abstract way and think about the symmetry stuff. So what the things I just mentioned. So maybe you can use even group theory, you know, I don't know, that's another direction to go, but I find it actually very fascinating because you're thinking about how these symmetries relate to each other. Okay. I'll mention, yeah, just here's a really nice argument for modularity, which comes directly out of the combinatorics. So remember, okay, if we have 4 inputs, so think of these as the inputs to like any network. Remember I said there are 2 to the 2 to the 4 possible functions. So that's 65536. Now, imagine I have a network. Let's suppose it only has 1,000 nodes, okay? Well, obviously 65536 is much greater than 1,000. So there's no way, it's impossible for me to get one realization of each function in the network, to have one node computing each of these functions. It's totally impossible. That also means I can't compute any complex functions. So it kills the possibility of getting complexity out of these inputs. Like my network just is totally hindered. However, I can split this input vector into 2 vectors of size 2. And this is a cartoon thought experiment, by the way. Things might be more complicated than this, but notice that now if k is 2, so I've split 4 into 2. Well, 2 gives me 2 to the 2 to the 2, which is again 16 unique functions. Well, if I split my network also in half, okay, so now I have 500 and 500. Well, 16 is much less than 500. So I can easily begin to think about getting complexity out of these 2 inputs, and so I've by splitting things, by splitting the inputs and by splitting the network, you could say modularizing the network and the inputs, I've suddenly changed my ability. I've increased the ability of my network to possibly do some interesting computation on the inputs. Okay, there's lots of questions you might have about that. It's just an initial observation, but it's a really nice sort of combinatorial observation for modularity, I think, which I'd love to investigate more. Let's see. Yes, okay, so here's something else that I think for me is quite interesting. There's talk of things like information engines, which usually means something a little bit different, but you can think of this network as almost like this cloud that's computing some information on the inputs. And I'll just make a quick point. So there's some information content to A and to B, the initial perturbation. They have already some information content. Okay, now if I look at these simple nodes here, most of them are actually losing the information. You could argue, yeah, well, of course, because they're not even connected to the network, but forget about that. Think a bit more abstractly for the moment. So most of them are actually losing information. However, there are some that are actually increasing the information because they're taking the information from A, the information from B, and they're combining it, okay? So that would be like your AND functions and your OR functions. Now, this is a bit of a cartoon example again, because this A and B are only 2 inputs. So normally you'd have a lot more. So it's kind of interesting because it's like this cloud of computation is happening, and most of it, so the cost of gaining some information, which is where you get your ANDs and ORs, the cost of that is that you actually have to lose a lot of information too. And that makes you start thinking about things like Liouville's theorem and maybe even Noether's theorem, which are related to the conservation of information and also have symmetry corresponds to conservation. So it starts connecting you to these deeper kind of physics theories, things. And so hopefully some of you will find that really fascinating. I do. And that's a whole nother chain of work to do. Yeah, so that's what I said already. Yeah, of course, you guys know a lot about transfer entropy. So obviously we didn't talk about that at all, but you could also, do transfer entropy measures on a lot of the things we've talked about today. I'll just mention quickly, I've done some work in the past about geographic networks where you lay the nodes out in a unit square, so they actually have a location. And then you restrict the connectivity geographically. It turns out you can still get large cascades even when the connection radius is quite small. So you're only allowing connections within a relatively small distance. But also when you do that, it's going to have effects on the modularity of the network. So I actually measured some of these things recently. So suddenly it forces your network to be not small world. So it won't have those long connections like you get in small world networks. Instead, it'll force it to be a lot more locally connected, which I think will then have an effect where if you perturb one edge of the network, I think you will get your complex functions being computed at the other edge of the network. Well, isn't that convenient if you're building a bunch of modules and you're putting them together in something like a brain, right? So then you'll have all these blocks which will compute the most complex functions at their outer edges. I believe that's what's going to happen. I haven't gotten to work enough on that yet, but anyway, that's a cool, hopefully interesting observation and something I'd love. But again, it's coming directly out of just the combinatorics of these things, really not, we didn't really impose anything else. Obviously, if you're talking about computation, you really need to show some kind of equivalence between these LTM models and the Turing machine. That's been done for things like recurrent neural networks. So that's something I'd like to do in the future. Yeah. Okay, quickly, I'll talk about consciousness. Now, remember in Tononi, I haven't read a lot of this stuff, but there's a lot of talk about integration of information. You will notice that these functions that we're calling complex, they have these paths from the different seeds. They are exactly integrating information. Okay, so you know that could be a nice framework to compare those consciousness types of models to this decision tree complexity and the complexity measures that we've been looking at. So that's just another thought. Anyway, that's probably more than enough. So yeah, there's some references, and thank you very much.
Okay, thank you, Galen.